Hello and welcome to the 41st lecture of Feynman Lectures on Physics. It is titled The Brownian Movement. In the first part of this lecture, I'd like to talk about equipartition theorem and its application to understanding galvanometers. How equipartition theorem tells us the fundamental limitations to sensitivity of a galvanometer. Then I'll talk about Johnson noise, which is always present in an electrical circuit at some temperature T. After that, I'd like to talk about thermal equilibrium of radiation, how we can understand what's called black body radiation from a classical mechanics point of view, and we look at how the classical mechanical treatment fails, and that leads us to the quantum mechanical approach. In fact, this was the first quantum mechanical calculation that was ever done, and it was done by Max Planck in December of 1900. And I'll end the lecture by talking about some random walk theory. Okay, so first I'd like to remind you what equipartition theorem is. It says that in thermal equilibrium, a system whose energy is the sum of n quadratic modes or degrees of freedom has a mean energy given by n times half kT. So as an example, think of a mass which is attached to a spring. This mass has energy given by the sum of its kinetic energy, which is half mv squared, and potential energy, which is half kx squared. So the mean energy is 2 times half kT. So what this theorem basically is saying is that if you have a spring which is connected to a mass, then even if I don't push on the spring, this mass would still fluctuate back and forth. And the reason why it would do that is because this mass is in contact with air molecules, which are constantly bombarding this mass left and right, so it starts fluctuating, and the amount of energy that is being imparted by the gas molecules on this mass is kT. Okay, next another example would be that of a monoatomic gas molecules, and a gas molecule has kinetic energy in 3 dimensions. So the energy of a gas molecule is 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared, and each component has an energy half kT associated with it, and you multiply it by 3 to get 3/2 kT, and that gives you the mean kinetic energy of a air molecule, gas molecule at temperature T. Okay, so equipartition theorem holds only when the temperature is very high, in the sense that we can ignore the discrete nature of energies, and we'll come back to this later. And it is also only valid when the harmonic oscillator approximation holds true. So we assume that the interactions of the system has a quadratic form, and it doesn't always have to be the case, and when it isn't the case, then equipartition theorem doesn't hold true. Okay, so now let's look at a concrete example of how equipartition theorem can be used in practical application. The first example that I would like to consider is the light beam galvanometer. So imagine there's a light source which is called L, which shoots light from it at a rate proportional to the current that is flowing in the circuit. So I can imagine there's a source of battery, there's some resistor, and then there's a light emitting diode at the bottom. And if I increase the current I, the amount of light that is coming out of this light source increases, and this light rotates the mirror, which is here, and this mirror is connected by 2 wires. It rotates the mirror, and the light goes from here to the scale. So if I increase the amount of light, the mirror rotates more, and I see a higher value on the scale measurement. It turns out even if there is no light present, we still see some fluctuations, some rotations in this mirror. And the reason is because this mirror is in contact with an environment. And this environment consists of air molecules which are bombarding the mirrors, and it is making the mirror wobble. And the question is, what is the mean angle that the mirror would rotate? And that we calculate using equipartition theorem. We say that the potential energy, actually the total energy of the mirror is 1/2 I omega squared plus 1/2 alpha, where alpha is the stiffness constant, theta squared. Now the stiffness constant alpha is just I times omega naught squared. So I'm going to plug that into this expression, and I know each quadratic term of the energy has an energy associated with it equaling half kT. So this has a mean energy which is half kT, and that's the expression you see here. I solve for average value of theta squared and I get this expression. So this tells me the magnitude of the thermal fluctuations in the galvanometer at temperature T, independent of any actual input, actual signal to the galvanometer. And this fluctuation is shown in figure B. Okay. So in this way, equipartition theorem sets limits on sensitivity of electrical instruments. Next is the concept of Johnson noise, which is the noise present in an electrical circuit independent of any signal in the electrical circuit. So the problem I want us to consider is the following. It's a series LRC circuit. Notice that this circuit has no batteries, no sources of energy. Even then, what would happen is that there are fluctuations in the voltages across the resistor, across the inductor, across the capacitor, and the reason is because the electrons in the resistor fluctuate because of thermal energy, and that creates a potential difference which is seen across the inductor and the capacitor. So anyway, so the question we could ask is, without going into the details of exactly what is producing these fluctuations, we could ask is what is the fluctuations in the voltage of the inductor? What is VL? So VL, it would be I, the current that is flowing in the circuit, times the impedance of the inductor, and the impedance of an inductor is J times omega L, where J is the square root of -1. So next I'd calculate what the current is, and the way we calculate current is by looking at the mean energy of the inductor, which is half Li squared, and equating it to half kT, and we solve for the average value of current squared, and then we plug it into the expression for current here to get average value of V squared, which is given by this expression. This is called Johnson noise. So notice that even though there is no voltage in the inductor provided by a battery, it still has a potential difference across it because of the noise, because it's in contact with an environment which is at the temperature T. Okay, next I'd like to talk about black body radiation. So this is a very important problem which actually led to the development of quantum mechanics. So the problem is as follows. Imagine we have a gas of atoms which are colliding with each other, and they are in equilibrium. Now if these atoms are at temperature T inside the then the electrons inside the atom will be oscillating with energy kT. And the way I got this is because I am assuming the electrons are in a harmonic potential, which is not true. We know it's a Coulombic 1/r potential, but the harmonic oscillator potential is a good approximation. for now. So the energy of an electron in an atom, we assume it's half mv squared plus half kx squared. And if we sum each mode has an energy half kT, and when we add the two we get kT. By the way, this k and this k are different. This is the Boltzmann constant times T, and this is the spring constant. Okay, so that's the energy in one dimensions of the electrons inside the atom. But the problem is, because the electrons are charged, as they oscillate back and forth, they radiate light and they lose energy, and thereby lowering its temperature. So we expect a gas of molecules at temperature T to keep cooling, and that's what happens. For example, on a stove top, it radiates light and loses energy and lowers temperature. Now, imagine, however, that there are mirrors on the wall of this gas of atoms. So the radiated light gets reflected back and scatters the electrons again. So there is a way to feed in the energy back to the electrons of the atom. But the question we'd like to ask is, what will be the energy spectra of the radiated light at thermal equilibrium, when the amount of energy which is being lost by the oscillators equals the amount of energy which is being absorbed by the oscillators. This problem is called finding the spectra of the black body radiation, and that's what we are going to do next. Our strategy would be to calculate the amount of energy that is being radiated by one particular oscillator per unit time, and then equate it to the amount of energy that is being absorbed by the oscillator from the surrounding light, and that would give us the spectrum of the light in the environment. Okay, so first we'll start by looking at the radiated light. So we assume that the oscillators, the electron oscillate in an environment, in an atom under harmonic oscillator potential, and so we begin by defining quality factor Q for the oscillator, which is defined as the energy of the oscillator divided by the energy radiated per radian. Let us call the energy of the oscillator W. Then energy radiated per radian is dW by d phi. I divide the numerator and denominator of the denominator by dt to get the following expression. So I have dW by d phi in the denominator. I divide and multiply by dt to get this. dW by dt remains as so. d phi by dt is omega naught, and that's how I get this expression. Okay, so now we know that the quality factor for an atom is given by this expression. This is a result which was derived in lecture 32, where R naught is the classical electron radius, omega naught is the frequency of oscillation of the electron, and if we assume that the wavelength of oscillation is in the hundreds of nanometers range, then it turns out to be 10 to the power 8. Okay, so we have a high Q factor oscillator, then this would turn out to be important subsequently. Anyway, so we solve for dW by dt and we get this expression, and then we plug in the value for Q, and then we finally get this expression for the rate of energy loss in the oscillator. Next, what we do is we average over time and use the equipartition theorem. So we are averaging over time. This prefactor is a constant, so it comes out, and the average value of the energy, the mean energy of the oscillator, is 3 kT. And the reason is because we are assuming that the electrons are part of a 3-dimensional harmonic oscillator. If it was a 1-dimensional harmonic oscillator, we'd have kT, but because it's 3-dimensional harmonic oscillator, we'd have 3 kT. Okay, so we have 3 kT here, and let me call the factors apart from this 3 as gamma, and so rate of energy loss by the oscillator is 3 gamma kT. Okay, so we have found how much energy is being radiated out. Next, we'll calculate how much energy is being absorbed by the oscillator. Okay, so let us assume that the spectral distribution of energy of light, which gives which gives the light energy density at frequency omega, be I of omega. Our goal is to find this I of omega. The cross section of oscillators at frequency omega is given by this. Again, this is a result which was derived in lecture 32. So an electron has a cross section given by this expression. Okay, since Q is large, we can approximate it as follows. Because Q is large, sigma of the cross section looks like this. If on the y-axis is sigma x of s, x-axis is omega, it looks like this. This part is omega naught. So we can write omega, we can replace omega with omega naught. So in the numerator and also in the denominator, omega squared minus omega naught squared is can be written as whole squared. In the denominator can be written as omega minus omega naught, which I'll keep it as so, and then multiplied by omega plus omega naught, which I'm going to write as 2 times omega naught whole squared. And then I simplify a little bit, and then I end up getting sigma of s is given by this expression. Okay. Now the energy absorbed by the oscillators per unit time would be the cross section, would be the energy density at a frequency omega times the cross section of absorption. So this is energy per unit area per unit time per unit and this is energy per unit area at frequency omega, and then this is the cross-sectional area. This gives us the cross-sectional area, and then we integrate over all frequencies, and that gives us the total energy which is being absorbed. Okay, I don't know the expression for omega, so that this is what we have to find out. We know sigma s of omega from lecture 32, so I plug that in, and I eventually get this integral. Okay. Now again, because this integral is so sharply peaked around omega naught, I'm going to assume I of omega is nearly constant and bring it out of the integral, and then I equate it to energy absorption rate. So I've done a few things here. I have brought everything in these terms, which are all constant, out of the integral, and I've also assumed that I of omega is nearly constant around the resonant frequency, around omega naught. So I've brought that out as well. Next, I do this integral from 0 to infinity. Because it's so sharply peaked, I can integrate it from minus infinity to infinity without changing the values much, and this turns out to be equal to I use the fact that integral from minus infinity to infinity of dx of x squared plus a squared is equal to pi by a to figure this integral out, and so in this case a is gamma squared over gamma over 2. Okay, so that's how we integrate this, and by equating it to the energy absorption rate, I end up with the final result, which is that I of omega is equal to omega squared kt over pi squared c squared. Notice we had solved this expression for a particular frequency of light, I of omega naught, but this is true for any frequency of light. So instead of writing I of omega naught, we can write it as I of omega. And this is the Rayleigh's law. This is the energy per unit area at frequency omega. Notice that this doesn't depend on the charge of electrons, it doesn't depend on the mass of electrons. So the expression for the energy density of light is independent of the characteristics of the oscillator that it is in contact with, and which makes sense. This is how it should be. It shouldn't depend on the nature of the oscillator. It is in thermal equilibrium with, it should only depend on the temperature, and that's what we see here. Okay, now here's the problem. I of omega is quadratic with respect to omega. So as the frequency increases, we should see more energy, more and more energy. So in X-rays, for example, the plot shows that the energy is much higher than the energy at, say, visible radiation. And so this tells you that if you this black body radiation would be very high in this ultraviolet regime, and this led to what's called the ultraviolet catastrophe, because when one does the experiments, one sees that actually while this result holds for low frequency, at higher frequency the curve bends down again and tends towards zero, as shown in the dotted lines. So we don't understand this on the basis of classical mechanics, and Planck had to invent quantum mechanics to explain this observation. Okay, so here's how we look at the same problem from a quantum mechanical perspective. We say that the oscillators, these electrons, cannot oscillate at any frequency. It can only oscillate at a certain frequency. So it can oscillate at it cannot oscillate, or it can oscillate at h bar omega energy, 2 h bar omega, 3 h bar omega, and so on and so forth, and nothing else. It cannot oscillate at 0.25 h bar omega energy. So we have discretized the oscillation rate of the electron, and this, it turns out, would solve the problem, as we'll see shortly. So Planck assumed that the harmonic oscillator can oscillate only with energy n times h bar omega, where n is a non-negative integer. The idea that they can have any energy is false. Okay, so again, we assume that the probability of a object to occupy an energy E is proportional to e to the power minus e over kt. In our case, energy is h bar omega, and let's call that x. Okay, the goal is to find the average energy of the oscillator at temperature T. Okay, so let us assume that there are n naught oscillators at energy E naught equal to 0. The total number of oscillators then is given by n naught plus n naught x. Remember, x is defined as e to the power minus h bar omega over kt. This is the number of oscillators in the first excited state. This is the ground state. This is the first excited state. This is the second excited state, and so on and so forth. We see we have an infinite series. The total energy of the oscillator would be the number of oscillators times the energy. So it would be number of oscillators is for the ground state is n naught h bar omega for the ground state. For the first excited state, the energy is 2 times h bar omega, but the number is n naught times x. This is the first excited state. For the second excited state, the number is n naught times x squared. but the energy is 3 times h bar omega. That's the second excited state, and so on and so forth. We have to add up the total energies, which I have done here, and then the average energy of the oscillator is the total energy divided by the number of oscillators. And if you plug in the numbers and simplify, you get h bar omega over e to the power h bar omega kt minus 1. This is the average energy of the oscillator. And so we replace kt, which we had earlier assumed that the average energy of the oscillator is kt, but it turns out it is not kt, it is this expression. And if you take the limit t tends to infinity, then you would see that this actually does tend to kt. But for small amounts, for lower values of temperature, we have this full expression, this what's called the Bose-Einstein distribution. Okay, so we replace kt with the average value of E we have calculated to get I of omega to be equal to this expression. So just so you know, we had calculated I of omega to be equal to 3 gamma kt, and I'm replacing kt with, it was this omega squared kt over pi squared c squared, and I'm replacing kt with the distribution that I've calculated here to finally end up with this expression. And if you plot this I of omega, it looks exactly as we see in experiments. It goes up and then it comes down. Okay. Next, I'd like to talk about Johnson noise, which we looked at earlier. So in this case, we'd like to write the power distribution of noise as a function of frequency, and the way we do it is we assume that we have an ideal resistor, ideal inductor, ideal capacitor, which is connected to a generator, a noise generator, which we imagine to be just a resistor, which we imagine it to be an antenna, which can be modeled as a resistor. So this is like an antenna. So as air molecules hit it, or light hits it, it starts fluctuating, and it can also radiate light out. So it can absorb light and it can also radiate light, and so it can set up a voltage across it, which leads to the voltage across the inductor, across the capacitor, across the resistor, as we had seen earlier. Okay, so how do we figure out what is the power distribution of the noise in the circuit? The way we do that is by using Kirchhoff's law. Kirchhoff's law says that the voltage across the resistor plus the voltage across capacitor and inductor must sum to the voltage across the generator. Now, voltage across the resistor is just IR. The voltage across the capacitor would be I times ZC, which is the impedance of the capacitor. Impedance of the capacitor is 1 over j omega C. VL is I times impedance of the inductor, which is j omega L. And so we solve for I to get this expression. Okay, next to figure out the power generated by the resistor, which is connected to the generator G, would be equal to an integral from 0 to infinity of I squared R. We have already calculated the current in the circuit here, and then we multiplied by the resistor value to get this expression for the power that is being generated in the resistor due to the generator G. Since we are assuming R is small, we have a high Q circuit, just as we had done in the black body radiation case. we can take Vg of omega, remember Vg is a function of omega, out of the integral to get this expression, and we can evaluate this integral. It turns out to have a value of pi over 2 RL, and this is the end result. Now this is the power radiated around the frequency omega naught, which is the oscillator frequency, which is the resonant frequency of the circuit. So I'm going to equate it to energy. So remember, I'm using gamma kT here because we are looking at one dimensions. The oscillations are in one dimensions, and I'm multiplying by d omega because that would give me the power in the frequency range omega naught to omega naught plus d omega. Okay, so quality factor for an RLC circuit in series is omega naught L over R. So gamma, which remember is omega naught over Q, becomes R by L. So eventually, once I plug in the value, once I equate this expression to gamma kT d omega, and I solve for Vg, I end up getting a power spectrum which is equal to 2 kT over pi times d omega. Again, notice that the power spectrum doesn't depend on the resistor value, it just depends on the temperature. Okay, so this equation is basically saying that in the range omega naught to or omega to omega plus d omega, this is the total power that is being dissipated by the resistor at temperature T. Okay. Again, notice that for high values for frequency, we would again have to replace kT by the black body radiation formula we had derived using quantum mechanics. So Johnson noise is basically equivalent to black body radiation. We use the same methodology. The idea is the same. It's just that black body radiation is in 3 dimensions. Johnson noise is in 1 dimension. Okay. The last topic which I would like to talk about is random walk. So the problem is the following. Imagine there's a random walker who starts out at point B, and he takes strides of length L at a random angle, independent of the angle at which the walker took the previous stride in. So it goes L distance here, then L distance there, and so on and so forth. And it reaches after 36 steps at the position S36. The question we could ask is, how far on average would S36 be from B? So we want to find this distance on average, because we can imagine in another realization of this motion, the random walker is starting at this point, and instead of going here like so, it could instead go like there, and then go there, and then there, and there, and then keep going, and after 36 iteration it could be somewhere here. So we want to sum over all the different paths and find the average distance we expect the random walker would be from his starting point. Okay, so that's the problem we want to answer, and the way we do that is by writing this relation. The radius vector after n steps is the radius vector after n minus 1 steps plus a length, a step L in along some direction L. So if I assume this is Rn, this is the position of the random walker from the starting point after n steps, and this is Rn of -1. This is the position of the random walker after n minus 1 step, and at the nth step the random walker goes in this direction. So we have Rn is equal to Rn minus 1 plus L. Now I squared this expression, so I get Rn dot Rn, which is Rn squared, equals, I squared the right hand side, I get Rn minus 1 squared plus 2 times Rn minus 1 dot L plus L squared, and then I realized that that Rn minus 1, the radius vector at Rn minus 1 is totally uncorrelated with the step that the random walker takes in the nth step. So the dot product, when I take the average on both sides, this term would be equal to 0. Okay, so what I eventually end up getting is average value of Rn squared is equal to average value of Rn minus 1 squared plus L squared. Then I can keep doing this for the smaller and smaller values of n. So I have similarly R of n minus 1 squared is Rn minus 2 squared plus L squared, and so on and so forth. I add up all the equations together. This would cancel out, these would all cancel out, and I'll have n terms in total. So I get average value of Rn squared is n times L squared. This fact that Rn squared average, the squared distance from the starting point is proportional to n, is a characteristic of Brownian motion. Okay, so this is what we get. Next, I would like to look at it in a continuous framework. So I'm imagining that there's a mass which is moving with some velocity v, and it experiences a drag force which is proportional to minus mu v, and then there's also some external fluctuating term. So the problem I have in mind is the standard Brownian motion problem, in which there's a big pollen grain which is present in in water, and this pollen grain is bombarded by water molecules on all sides. So that's the force produced by the water molecules on the pollen grain is F external. The drag force is mu times v, and and then I use F equals ma to get this expression. So just let me write down how I got the first expression. F equals ma. The forces which are acting on the system are the drag force, which I'm calling minus mu dx by dt, plus the noise force from the water molecules. Okay, then I multiply by x on both sides, which I've done here, and take time average. Now this term x times F external would be equal to 0, because the force is not correlated with the position. So when I take the product, I get 0. They're uncorrelated. Similarly, the average value, it means the average value of the force is 0. That's what it actually means. Wait. So yeah. So why is it 0? Let me think. Yeah, the reason why it's 0 is because the force is independent of position, and so we can write this average value of x times f as average value of x times average value of f external, and so this is equal to 0, because average value of f of the noise force is 0. The second term can be written as d dx of x squared. The first term, after you do some simplification, you basically use the fact that x times d2x by dt squared is equal to ddt of x times dx by dt minus m dx minus dx by dt squared. Okay, so once you write it this way, you see that again this term would cancel out because position and velocity are uncorrelated with each other, and you just have the second term, and so that's how you get minus mv squared plus mu by 2 d by dt of x squared. We solve for d by dt of x squared and we get this expression. In 3 dimensions, we have r squared, which is x squared plus y squared plus z squared. So we have this equation in all 3 dimensions. We add them together to get r squared is 6 kt over mu. Because this is a constant, we have also integrated, and we get a time t on the right hand side. So what I have basically done to get this expression is integrated this expression to get average value of x squared is equal to 2 kt over mu times time t, and I have similar expression for y and z, and I've added them together to eventually get this expression. So this expression was actually instrumental in calculating the value for Boltzmann constant. We know mu from experiments, we know r, we can calculate r, and if we have the value for r and mu, we know temperature and time, we can figure out the Boltzmann constant. And once we have the Boltzmann constant, we can figure out Avogadro's constant. That's why this problem is of great historical interest. In fact, it was first calculated by Albert Einstein in his PhD thesis. Okay, so that's all there is to cover in this lecture. I'll see you next time.